Hi, good morning, everyone. Good morning, guys.
Hi, madam. Good morning.
Okay, thank you. So I hope that you guys can hear my voice. All right. So,
Can.
all right. Thank you. How are you guys? How's everyone?
Yes.
Okay, thank you.
Fine.
Right. Okay. So, as for today, we will have our tutorial 2, Unit 2 of M internal circuit structures for analog electronics. And as for today, can we go for the lecture first, and then at the end we will discuss on the uh, lab session for next week. Is it okay with you guys?
Yes, madam.
Okay, thank you. All right. So I hope that you guys can see my screen. Unit 2 is on op-amp internal circuit structures, and these are the objective for this tutorial 2. Okay. We will cover on the current mirror circuit for BJT and MOSFET, and then we will go for differential amplifier, and towards the end a bit on the internal structure of 741 op amp. Okay, first is on the current mirror circuit. Basically, for today's tutorial, we will have 3 subchapters. First is on the current mirror circuit, second is on the differential amplifier, and the third one is on the op-amp circuitry. Alright, for the current mirror circuit, we will cover on the BJT and some on the FET. Okay, for the voltage gain, we have the AV voltage gain. Voltage gain is equals to V out over V in, basically. Of an amplifier is dependent on the, if we use the BJT, it is depend on the collector resistance RC and also on the beta value. Inside comes together with the BJT, the transistor. And if you use the FET, it is depends on the transconductance GM and also on the drain resistance RD. Okay, for active float design is necessary and is used to overcome for the limitations. Operation amplifier is very high. Gain stage of the operation amplifier is very high. Moreover, for the resultant voltage level is undesirable and it is impractical to achieve. For example, if we have 1 milliampere of collector current flows in the collector resistance of 100 kilo ohm that require 100 voltage drop. If the 20 volt AC peak to peak is needed, then the supply voltage has to be at least 120 watts. So this is, you can say that it is undesirable. Okay, so this is the basic current flow circuit using bipolar junction transistor. We have the, I hope you guys still remember, this is this is collector, this is base, and this is emitter. Okay, the current source whose output resistance normally is high, which is depending on the early voltage or the VA. Or we can also say is the VM. Okay, it's used to replace the collector resistance or drain resistance. So from this flow here, we can say that IR, this one IR is equals to VCC minus VBE. Where is the locations for VBE over the value of the resistor? Okay, VCC this one. VBE is in here. VBE. Okay, so it will flow through this, the path. Okay, why? it will flow by this path rather than this path, because we know the value for VBE is equals to 0.7. For this path, this is, we write it as number 1, loop or path 1. For number 2 is VCC minus VCC plus IRR plus V. For here we have VCE plus minus VCE equals to 0. Okay. For equation number 2, it is actually the same one. If we do the equation number 1, minus VCC plus IRR, this one, and then go by this plus VBE equals to 0 because the emitter is connected to the ground. So it is equals to 0. You can say this is actually closed loop. So for this equation, we know the value of VBE, and VCC is also, we already know. So R is given. So we do not have the value for the current. So we can use this equation, the first one, okay, the red equation. For the second equation here, we do not know the value on the VCE. It is not 0.7. 0.7 is for VBE. So IR is also the second unknown that we do not have the value. So we cannot use this equation. Okay, equation number 2. So it is easier to use the equation number 1. Unless we have the value of the IR, then we can use this one. Okay. So in the basic concept of KVL, I just want to show some here. To apply for the KVL, actually, we must it is not consider, it is assume that the VCC is connected to the ground. So this one is also connected to the ground. So it is actually indirectly connected to here. That is why if we do the KVL by this and then back to this one, it is closed loop. Okay, minus VCC plus IR goes to this way plus VBE to the ground and then is it back. Okay, so this is the basic concept for KVL. Okay. So now we have the equation for IR here over R. And then we can say that IR is equals to IB plus IC because over here we have IC and IB. So meaning that IR is equals to IB plus IC. And then we know that IC is equals to beta IB, the assumption. So we can say that IR replace inside here. Beta plus 1 IB. Okay, replace this beta IB in the IC. So we can have IR equals to beta plus 1 IB, or also equals to 1 plus 1 over beta IC. Okay, for larger beta value, much more larger than 1, the collector current IC is approximately equal to the reference current IR because we consider IB is too small, approximate to 0. Okay, so we can say that IR is equals to IC if the beta value is very large. Okay. The next one, we go for this two transistor current mirror design. Okay, for this one, we assume that the Q1 and Q2 assume to be similar in parameter, meaning that all the parameter in these two resistors are same. Okay, so this is the equations for IC. Okay, if these two transistor Q1 and Q2 are similar, so it will have the same value for this current mirror circuit using two NPN transistor, because this is goes out. So meaning that these two Q1 and Q2 is NPN. So if these two are similar, so VBE1 is equal to VBE2. And also IB2 equals to IB1. Same goes for IC1, IC2 equals to IC1, IE2 equals to IE1. And from there, we can say that the IR is equals to VCC, if we do the KVL actually, minus VEE minus VBE over R. It can be from this one, goes here, this way, or this way. Same thing, because these two resistor is the same. So minus VCC plus IRR plus VBE, can be either VBE1 or VBE2, same value. And for here, it is not ground, it is VEE. So we have value for this. Plus VEE equals to 0. Why this one is plus? Because we connect to the positive side here. And then negative will go to ground. Same goes here. Positive, negative goes to ground. Okay. So when we put it this IR in one side and all the other components the other side, then we can have these expressions in order to get the IR value. So for the IR here, IR, we can say that 2IB plus IC, because we have 2IB here. IR, this one is IB1 plus IB2 for this path. That is why 2IB, same value. If it is 2 milli, then this one is also 2 milli. So IR is equals to 2IB plus IC.
Miss, can you explain again the 2IB?
Okay. I erase this one first. Okay. This one, I hope you understand on why all the parameter for these two transistor is same, because it is identical transistor. Okay. Why it is 2IB? Because now let's say IR is this one IR. So dia akan pecah kepada two paths. One is this way, one is this way. Goes down, horizontal and vertical. This one is IC2 because it is at collector. This one is at base. Base for Q2 and also base for Q1. Okay. So for Q2, we have IB2. For Q1, we have IB1. This IB2 and IB1, it has similar value. So meaning that this one here, okay, meaning that at this point, at this point, it is actually IB1 plus IB2. Sebab dekat sini dia pecah, pergi kiri satu, pergi kanan satu. So for this one, kat sini pun sama. This is same value. IB1 plus IB2 equal to 2IB. Why? Because it has same value. Let's say, contoh, now it is 1 milliampere. For here pun 1 milliampere. So for this point kat sini, yang atas it is 2 milliampere lah, kan? Okay, faham tak? Is it okay? Get it?
Yes, thank you.
Okay, welcome. Alright, so that is why here we have 2IB because it is identical transistor. Plus with the IC, this one. Okay, because tadi yang saya tulis kat tepi ni, it is IC1 is equals to IC2 and then we can say it is actually IC. Sama je. Same goes with the IB. That is why kita tulis IB saja and this one is IC sahaja. Okay, and then we can use the relation. IC is equals to beta IB. Okay, and then here we have IE. Okay, for the IE is equals to beta plus 1 IB or IE is equals to betul lah, IB beta plus 1. Okay, so that is how when we this one is when we replace with the VCE and on the IC1. Okay, from here. Okay. All right. So this is the AC analysis for this current mirror circuit. This AC analysis, we have two this one, we have two transistor Q1 and Q2. Okay, so for this AC analysis, it has this is for CBE is for the first Q2 at the left side, this one Q2. Okay, this one Q2 and this is Q1. It bertindih redundant at the base. Same goes here. This is Q2 and this is the other, sorry. The other side is Q1. Okay, it has connections at same node for base. That is why here we have C. This is actually for C2. This is for C1. And this is for base 1 or base 2. Okay, we can write, draw as this one. And same goes with E. We have only, this one is E for 1. This is E for 2. And then it connect to the ground together, meaning that it is has the same node here. That is why we have the same 1E only for Q1 and Q2. Okay, what are the parameters that do not connect in here is the RO2, RO1. Okay, this one. And okay, this is R52 for Q2, this side. And R52 for Q1 from this side. Okay, this is the current mirror for this two transistor BJT AC analysis. Okay, and for here, for the R in is from this view, this is for R out from this view. So for the R inward, do we have R, this R, parallel with small r naught, and then parallel with R phi 2 when we uh, measure for the input resistance, this one will be open circuit. Okay, so we can have R naught 2 parallel with R phi 2, and then parallel with 1 over GM2. Take into consideration for this one, since open circuit, then we consider as replace with the transistor. Since we have the current source, so for the transistor is V over current. Okay, 1 over GM2. And for the V out, for the R out for this output resistance is equals to, what do we have here is the small r naught 1. Okay, for this one, because this is at this area, it is open circuit. Okay, for the V out is equals to GM1 VBE1 R out 1, because V out is at this port, at the V out port. This one is reflect with the Q1, so we have the Q1 parameter. Okay, so this is for next one. We have the Widla current source. Also, it is actually also comes from the mirror current, but then we have the resistor here. Okay, the current mirror made of two lateral. This one is two lateral NPN resistor, has limitation due to low beta and lower early voltage. Thus, it has lower current carrying capability and less output resistance. And the limitations can be overcome by using three transistor designs such as Widlaw, Wilson, or cascade current source, which has higher output resistance than two transistor current mirror. Okay, this is the first method is Widlaw current source, and we have the RE here. This is the expressions for the RE. For IR, we can say that IR is equals to IC2 plus IB1 plus IB2. IC2, this one is IB1 plus IB2, or also equals to IC2 plus 2IB. And IR equals to VCC minus VBE2 over R. Okay, for this, for this one, it is actually not identical for Q1 and Q2, so we cannot use the second one. Okay, it has slightly different on the Q1 and Q2 for Widlaw. Okay, for VBE, since it is not identical, because we have this one here, VBE2 is equal to VBE1 plus IB1 plus IC1 multiplied with the RE. Okay, it has slightly different value. Okay, and the relation of the beta equals to IC plus IB, and also IE equals to beta plus 1. IB is still similar. Okay, so this one is the AC analysis for Widlaw current source with the existence of the RE here. Okay, the first part this one is for the Q2 and this one is for Q1. For the RI, Rin are parallel with small r naught 2 parallel with 1 over GM2 for this one, parallel with R phi 2. Okay, for Rin. And we have the R naught, I read it here, R out is equals to R naught 1 parallel with, plus first, R naught 1 plus parallel of R phi 1 with we have the RE. These two. We consider it is as parallel because this one, if we want to get for the output resistance, we consider as connected to the ground. So this one is connected to the same node from here, goes to the ground, same goes with the RE. So parallel R phi 1 with the RE. Multiply with the 1 plus GM R naught 1. Okay, approximate with the RO1 1 plus GMRO1. Because this one is approximate to unity, 1 equals to 1. So this one is approximate to RO1. Okay, for this one only. Because sometimes value of RE is a large number. Okay. So next we go to the second method. This one is the first one. Okay, this is the Ritla is the first one. So next one we go to the Wilson BJT3 transistor method. So this one we call it as the Wilson current source. For the IC1, we have the IC1 here. IC1 is equals to beta square plus 2 beta over beta square plus 2 beta. Beta square plus 2 beta over beta square plus 2 beta plus 2. And for the R out is approximate to beta R out over 2. Actually for this IC1, it has lagi kat belakang ni. I have to erase this first. Panjang sikit. Okay. I write this at the top. IC1 is equals to beta square plus 2 beta over beta square plus 2 beta plus 2 multiplied by VCC minus 2 VBE over R. Okay. Other cascade current source such as a current source with gain are commonly used too. And not to worry because for this Wilson current source, we are not going through the AC analysis for this one. Okay, because we have three transistor here. So for the AC analysis, it might be a bit complex. Okay, for other cascade, we also can be used, and the current source repeater utilizing multiple transistor, it is used to provide multiple current of equal magnitude for equal transistor. Okay, this one is for current repeater circuit. Okay, practically it uses multiple collector transistor to converse the area. Okay, for this one is enable multiple desired current source. Yes. Okay, by adjusting the base width and cross-sectional area. So for the current IR is in this one, in the current flow at the resistor R. This equals to IC1 beta 1 over B. Okay, for this equals to this one, also equals to this one. And if we have up until N transistor, also is equals to the same value. Okay, but then please remember that IR is not equal to IC1, also not equal to IC2, not equal to ICN. Okay, because the transistor have equal cross-sectional area. Okay, if for this one, if it do not if the transistor have equal cross-sectional area, if for this one, okay, it doesn't have equal cross-sectional area. So it depends on the parameter of the transistor. Okay. For MOSFET, current mirror circuitry has some function as its bipolar junction transistor counterpart. This is if we use the MOSFET. Okay, the BJT current source can be converted to an equivalent MOSFET current source by assuming that the beta value is infinity. Since the gate of the MOSFET do not allow any current, there is no need for the base current compensation. So this is the basic current mirror by using MOSFET. Okay, just now we have the Q1 and Q2 for BJT. For MOSFET, we have M1 and M2. Okay, it is assumed that for both M1 and M2 is identical for current mirror. Okay, and since for the FET, we have the VGS. So this is drain, this is source, this is gate. So we consider as the VGS1 equals to VGS2. And for the IR here is equals to ID2 because there is no IG equals to 0. Okay, by default it is IG is equals to 0, so IR equals to ID2. And this one equals to VDD minus VSS, we have the value, minus VGS 2 over R, the whole thing over R. Okay, if we do the KVL. Okay, it will flow. Alright. So this is the current ID1 can be controlled by altering the width of the MOSFET transistor for M1. Okay, so this one also, we are not going for the AC analysis for the MOSFET. Next is the Wilson MOSFET. Just now we have the Wilson BJT. Now we replace the BJT with the FET, the MOSFET. So we have the M1, M2, and M3. Okay, it has improved the output impedance than the earlier version as we use the BJT. So for the IR, we can write as IR equals to VDD minus VSS. VSS, we have a value, minus VGS1 minus VGS2 over the whole thing over R. IDD. Okay. Or it can also goes this way actually. Okay, so this is for the Wilson MOSFET for current mirror. And this is just to show for the AC analysis. This one is we have G1, and also on the 3. Okay, it is by this way actually. Take into consideration for this one because we have the gate 1 and 3 only at the node 1 and 3. Okay, for the AC analysis small signal model for MOSFET current mirror. Okay, next one. We have the MOSFET cascode. Now we have 4 MOSFET, M1, M2, M3, and M4. Okay, these configurations has better output impedance, meaning that the R out is better value or larger value. For identical MOSFET, whereby the output impedance are the same, which we have the R0. If it is identical, meaning that it has similar property, R01 equals to R02, and we can say it is equals to R0. And for the R0 value plus okay, just use this one. For R0 value, output impedance is small R0 1 plus GM1 R02 plus R02, meaning that it take into considerations for this part. Okay, for R0 output port. Okay, next one, we have the active load and diode connected for the circuit. And for these connections, we have Q1, Q2, and Q3. For BJT, we consider the Q2 and Q3 act as the active load for this upper part here. And Q2 and these two also has equal geometry and design parameter, meaning these two is the identical transistor. Okay, and we have the Q1 connected with the source. So this is the output impedance and the voltage gain. Okay, not to worry because normally for these types of circuit, you only need to know normally only ask on the characteristic of the circuitry. Okay. Next one is we go for the differential amplifier. Okay, we will discuss on the differential amplifier by using the BJT, JFET, and might be on the MOSFET. BMOS, I don't think so. Okay, on the AC and DC analysis as well. Okay, differential amplifier or diff amplifier is a multi-transistor amplifier. It is a second stage in the op-amp, and it is the fundamental building block of analog circuit used to provide high voltage gain and high common mode rejection ratio CMRR. Okay. It can operate in two modes, namely common mode and differential mode. Okay, if two input voltages are equal, the differential amplifier gives output voltage of almost 0 volt. There is no value at the V out. If two input voltage, we have V1 and V2 considered as the V plus and V minus are not equal, the differential amplifier gives a very high gain voltage. That is why we call it as the differential amplifier. So this is types of differential amplifier by using the BJT, bipolar junction transistor. We have Q1 and Q2. on the connection, it is not similar as the current mirror just now. Consider an emitter coupled bipolar junction transistor differential amplifier, and then for this circuit we assume this Q1 and Q2 are almost identical and have similar parameter. So we can say that for this one we have IE at this part is equals to, we can say it is actually IE1 plus IE2. If it is identical, then it is equals to 2IE. IE at this bottom here. Okay, and this is for the DC characteristic for DC analysis. Okay, Vin 1 is equals to, because we have two, V in 1 and V in 2, V out 1 and V out 2. V in 1 is equals to, oh sorry, okay, V in 1 equals to V in 1 minus VBE1 equals to V into minus VBE2, because it is identical. And we have the pure saturation current, and for here VT is the thermal voltage. VT thermal voltage approximate to 26 milliwatt or sometimes 25 milliwatts at 300 Kelvin. And what else do we have? VEDM here is the differential amplifier. Vout DM is a Vout differential output voltage. Okay, since we have the DM, so AV will be the AVDM, Vout over Vin. Okay, it just from this analysis we use the same circuit as just now, but then we replace, or this one not considered in the circuit, okay, for this port, because this is very large value, so the current will flow here, so consider as this is as the same node, so there is no not considered in the analysis for the DC analysis. So this one is some differential mode voltage gain. Also we have the common mode voltage gain and the common mode rejection ratio for this circuit. Okay, so next one we have the JFET differential amplifier. Since the JFET has very high impedance, it satisfies the high impedance and low input bias current requirements for the differential amplifier. For this one here, we have the JFET M1 and M2 in the circuit. It has the same parameter, also identical. But then since for the JFET, IG is equals to 0. And we can say that the IS is equals to ID1 plus ID2. IS in here, this one, equals to ID1 plus with ID2. And for the V out 1 equals to VDD minus ID1 RD. For V out 2 equals to VDD, V out 2 or V out 2, is this the same, yeah? VDD minus ID2 RD. Okay, with respect to the out 1 and out 2 here. And for V out dm is equals to V out 2 minus V out 1. Because we have two stages here. Okay, 1 and 2. So this is for V out dm. Comparisons or differential drop between these two V out. So this is for the AV voltage gain for differential mode and common mode voltage gain and with the common mode rejection ratio. The next one we have the MOSFET differential amplifier. It's slightly same thing as previous, I think. Oh, sorry. This one is we use MOSFET. Just now we use the JFET. Okay. So this is for, we change the MOSFET M1 and M2. Okay. We will, this one is just to show to you guys that we can change the JFET with the MOSFET. Okay. And this one is the big MOS. Big MOS. The combinations between the BJT with the MOSFET. So we call it, the name is the big MOS, differential amplifier. So we have the M1 and M2, the MOSFET. We have Q3 and Q4, BJT, and M5 is the MOSFET as well. Here is the current and resistors for each of the node. Okay, for BJT, we have IC and ID for the MOSFET, reflect with the node of the terminal for each of the transistor. Okay, also we can get the DC characteristics. All right, so next one we have we go for the op-amp circuitry. Okay, op-amp circuitry explains on the design of the big MOS. Also, we want to go to the 741 bipolar junction, bipolar operation amplifier. Okay, so for here we have the operational amplifier is a direct couple high gain amplifier used to perform a high variety of a function, which is often referred as the linear integrated circuit. So we have few stages here. First is on the differential amplifier in the block diagram here. Differential amplifier used as the input stage to provide inverting and non-inverting input, high common mode rejection ratio, high input impedance, and high voltage gain. Okay, next one we have the gain stage. The signals will go to the next stage is the gain stage. Second voltage gain stage used to provide common collector and common emitter voltage gain and also frequency compensation. Okay, next one is on the level shifter. The level shifter we use to adjust the DC voltages so that the output signal is reference to the ground. And finally goes to the emitter follower. The output stage of the op-amp contains mainly an emitter or source follower circuitry which has a class A, B common collector or common source. Okay, for the class of the amplifier, we have class A, class B, class AB, and class C. That one we will discuss in tutorial 3. Okay, so this is a circuit for big MOS Miller operational amplifier. Okay, inside this circuit we have the capacitor. COM is a compensation capacitor used to improve the bandwidth of the amplifier at high frequency. Okay, we have the M11 first is M11 PMOS. Okay, because PMOS, the error is goes into the transistor. If it is goes out, it is NMOS. PMOS M11 and NMOS. This one is NMOS. This is PMOS. Okay. M11 is PMOS. M12 is NMOS. Form the voltage divider circuit that provide voltage bias for PMOS M8. This one. Okay, we have the voltage bias. The gate to source voltage PMOS M8 is equals to V bias minus VDD. Okay, gate to VGS of M8. VGS M8. For identical MOSFET, the current in NMOS M1 and M2 in here, it actually comes from the concept of current mirror. Okay. For identical MOSFET, the current in NMOS M1 and M2 shall be half of drain current ID5 from here. Okay. Alright, let's see on the characteristic. Okay, we have the V bias for current transistor for the MS and this is M4. Okay. Okay, this is for for this is the first stage, this is the second stage. Okay, in divided by here. Okay, this one is for the second stage, and we have the overall voltage gain. Okay, the overall voltage gain AV for these two stages, stage 1 and stage 2. Okay, next one we go for the 741 operational amplifier. Okay, I believe that you guys, all of you familiar with this operational amplifier, or sometimes in layman term or simple word we call it as the IC. It is a general purpose of op-amp designed with bipolar junction transistor BJT. Mainly have the differential amplifier mid-stage voltage gain and output high current common drain amplifier. Okay, analysis of impedance, current sourcing or sinking and voltage gain of the various stages of the 741 bipolar BJT op-amp. We can consider as these types of circuit here. Okay. The differential amplifier stage of operation amplifier is the input stage used to provide inverting and non-inverting input, high common mode rejection ratio, high input impedance and voltage gain. I hope that you guys still remember what we have learned in tutorial 1 on the inverting and non-inverting with the two input. Okay, so this is the differential amplifier stage circuit. Okay, the differential amplifier stage of op-amp if the input stage used to provide inverting and non-inverting with the common mode rejection ratio value. We have BJT1 and BJT2. Okay, so this is the characteristics of the DC analysis of the differential amplifier. We have the differential mode AVDM and also common mode AVCM, and this one is CMRR, common mode rejection ratio. And this one is the differential input impedance at the input port, okay, due to the differential amplifier. Okay, this is the internal circuitry for 741 op-amp. consists of common collector, common base, amplifier circuit. Common collector and common base amplifier. We have the Q1 and Q2 at the top here. Q1 and Q2 form common collector amplifier with output fed to the common base Q3 and Q4. Okay, the collector resistance is an active resistance for Q5 and Q6. Okay, so we have the active resistance at L or the active load. The amplifier is fed with a constant current generated by a current source from Q8 and Q9. We have the Q8 and Q9. Okay, current source. So this is the internal circuitry of 741 op amp. Next one, this is a bias analysis. Okay, with the reference circuit or reference current circuit. It is actually a constant value. The reference bias current circuit different bias current IF is generated in the branch composed of two diodes connected with the Q11 and Q12 and with the resistance of the R5. Okay, this one, resistance of the R5. Okay, this one is for the voltage gain and impedance analysis. The NPN, PNP transistor combinations of, we have Q1, Q2, Q3, and Q4. It forms the active element of the differential pair. The active load are provided by Q5, Q6, and Q7. Q5, Q6, and Q7 considered as the active load. And transistor Q8 and Q9 from the current mirror at the where is the Q8 and Q9? Q8 and Q9 from the current mirror to bias the base and to ensure the transistor are remain in the active region when there is no input signal. Q8 and Q9 at the top actually. Okay, this one eh? Okay, so this is the AC equivalent circuit of 741 differential stage. And this is the Thevenin circuit for the 741 equivalent circuit. Okay, the AC pi model of the common base amplifier for the emitter resistance, which is the input impedance of the common base amplifier. And the Thevenin equivalent circuit of the common collector stage, which has transistor Q2 in the, we have this one due to the Q2. So that is why VBE2 alpha 2 GM2. Okay. And this is for the voltage gain and impedance analysis. It is actually fixed value, okay, for the R out, output impedance, and the V out. And this one is a voltage gain for emitter follower. We have two stages, AB1 and AB2. This is small value and this is huge value, but then in different polarity with the phase shift different. Alright, so this is the AC circuit analysis for voltage gain 741 operational amplifier. Contains the current source, common collector, and common emitter cascade configuration. Simplified schematic circuit of the voltage gain here. Okay. This is the AC circuit of voltage gain for V in and resistance RS. We have the V in and resistance RF. Represent the Thevenin equivalent circuit of the differential stage as measured earlier. So this is for AC equivalent circuit. This one, the AC equivalent circuit with the V in and RS value. Okay, next one is on the DC level shifter. Inside the block diagram just now is a level shifter. This is especially important for the output to be close to zero when there is no input signal and as the input for the next stage. The DC level shifter utilizing the VBE multiplier. Okay, with the Q1 and Q2 VBE in here. Okay, VBE multiplier concept. This is just the same thing as this one here. And this is for emitter follower stage. This is actually at the final stage. Okay, the output stage of an op-amp is capable of supplying the external load current and must have a low output resistance. Let's see on the circuit, this one here. Okay, contains a class AB and with the network Q18, 19, and 10. This one. This is actually, we call it as the class AB operational amplifier. Rather than using two diode network to bias the output transistor for Q14 and Q20. At this, sorry, Q14 and sorry, not that one, Q20 and okay, this one. Okay. And beta value for NPN, NPNP transistor at the output stage shall be 250 and 50 for the beta value. Okay, so this is the output stage of 741 op-amp including level shifter and also on the protector circuit. This is considered as the protector circuit. Okay, so for the output short circuit protection, this one is the explanations on the short circuit protections. Most operational amplifier include the design in output short circuit protection. Transistor Q15, 21, R6 and R7. This one, 15, R6, R7, 21. From okay, so this is actually this is not this one. Okay, this is from the protection circuit. And the emitter current of transistor Q14 and 20 is more than 20 milliampere. The voltage developed across the base to emitter for Q15 and Q21, this one, base to emitter for these two. Okay, and then the voltage for Q15 and Q21 will be more than 540 milliampere and sufficient to turn on for the Q15 and 21. Okay, so this is, you guys can read from here the output short circuit protections explanation for this output emitter follower stage. All these circuits is actually inside the block diagram. Block diagram for each of the stage actually. Okay, this one. Okay, inside this block diagram. Right, so that's all for the tutorial 2. Okay, for next tutorial 3, we will cover on the class amplifier, class A, class B, class AB, and class C. Okay, is there any questions from you guys?